Example, we have butadiene. Butadiene dimerizes, and dimerization means that two molecules of something stick together. Butadiene dimerization was studied, and the following kinetic data were obtained. Okay, so let's go ahead and write out the formula. 2C4H6 turns into C8H12. Okay, so now we have our time value. I'm going to go ahead and write it as one big plot. So our time value, we have our concentration of C4H6, which is our reactant. Now, so what we want to do here is we want to find the rate constant, we want to find the order of the reaction, and we want to find the half-life. I'm sorry about it. I should have actually told you what it is that we're actually going to be doing here. So the first thing we want to do is we want to find the order of this particular reaction based on the data that we're given. And then we want to find out what the rate constant is, and then we want to find out what the half-life of the reaction is based on this data. So T, let me go ahead and write this down. It's 0, 1,000 seconds, 1,800, 2,800, 3,600, 4,400, 5,200, and 6,200. And what we have is 0.0100, 0.0625, 0.0476. No, that's not right. That's 0.0100. So this is going to be 0.00625. The butadiene is diminishing. 0.00476, 0.00370, 0.00313, 0.00270, and we're almost done, no worries. 0.00241 and 0.00208. Okay. Given this raw data, find the order of the reaction, find the rate constant, and find the half-life of this reaction based on the fact that we started with 0.0100 moles per liter of this butadiene. All right, so we need to check, is it first order or second order? So we need to plot both the logarithm of C4H6 versus time and the reciprocal of C4H6 versus time to see which one of these gives us a straight line. If this gives us a straight line, the logarithm, it's first order. If this one gives us a straight line, it's second order. That's how we do it. Okay, so here's what the data looks like. Let's see, let's do logarithm first. So we get minus 4.605, minus 5.075, minus 5.348, minus 5.599, excuse me, minus 5.767, minus 5.915, minus 6.028, and our last one is minus 6.175. Reciprocals are a lot easier. What we have is 100, 160, 210, 270, 320, 370, 415, and 481. Okay, so now we're going to plot, put in blue, we're going to plot this versus time, and we're going to plot this versus time to see which one gives us a straight line. So let's go ahead and take a look at what these plots look like. I'm going to go ahead and put them next to each other. So I'm not going to give you too much detail on these graphs, you can actually go ahead and plot them yourself on a piece of graph paper or using any software like Excel or something like that. What you're going to end up with, as it turns out, let's see here. This is going to be 200. Yes, so let's do the logarithm of the butadiene versus time here, and let's do the 1 over the reciprocal of butadiene, which I'll just call A, over time here. When I do this, the logarithm graph gives me something like this. Definitely not a straight line. When I do the reciprocal, I get a straight line. So I will have you confirm this, but this is exactly what happens. So because it's the reciprocal that gives us a straight line, it's a second order reaction. Second order. So we can go ahead and write the differential rate law. C4H6 dt equals the constant times C4H6 to the second power. We know it now, it's a second power. We derived it from the graph. Now, so we have an order of 2. Now, the next thing we want to know is, what is the rate constant? Okay, well, the rate constant, the best thing to do is to go ahead and, let's see, how shall we do the rate constant? Let's just go ahead and use the integrated rate law. So we know that the second order is 1 over the concentration of A equals minus K. Actually, you know what? What am I saying? Let me just, well, you know what? Let me write it out so we have it. Equals positive K times T plus 1 over A0. This is y equals mx plus b. We just graphed the reciprocal over that. We got a straight line. So now what we want to do is we want to pick 2 points on that straight line. Take the delta y over the delta x of those 2 points. And again, the points need to be on the line. If the data points that we have in the original data when we calculated it are on the line, that's fine. You can use those data points, but if they're not, make sure you're using points that are on the line. When we calculate delta y over delta x from this graph based on the kinetic data that we derived, we end up with the following. Let's see. Let's use a couple of points actually. So let's use delta y over delta x equals, as it turns out, a couple of the data points do fall on the line, so I pick the first and the last. So it's going to be 481 minus 100 over 6200 minus 0, which gives me 0.06145, and the unit is going to be liters per mole seconds. I know the units for these rate constants don't really make sense. They tend to change depending on what order it is. It's actually the number that matters. So this is our rate constant. And now we want to find T 1/2. Okay. Well, T 1/2 of a second order reaction is 1 over K times the initial concentration. It's equal to 1 over 0.06145, and the initial concentration was 0.0100. So when we do that, we get 1627 seconds. So there you go. Raw data, time concentration. We calculated logarithm of concentration. We calculated the reciprocal of the concentration. We plotted ln of concentration versus time for one graph. We plotted reciprocal of concentration versus time for a second graph. We saw which one of those graphs gave us a straight line. In this particular case, it was the reciprocal versus time that gave us a straight line, second order. Because it's second order, I go ahead and I can write the differential rate law if I need it. We need the rate constant, so I just found a couple of points on that straight line. I took the slope, y2 minus y1 over x2 minus x1. I ended up with the rate constant. And then, because I have the half-life formula, I have the rate constant which I found. I have the initial concentration, which is the initial concentration from raw data. I was able to calculate the half-life of this reaction. Very, very straightforward. Nothing altogether too complicated. Again, differential rate law, integrated rate law, half-life. Those three things are what's important as far as the kinetics of a reaction are concerned. Okay, that was second order.